think we're good. So we were talking about energy methods, right? We have been talking about energy methods for last, well, 2 weeks, excluding the exam, last 2 lectures. Now, we're still going to talk about energy methods, but we're going to be more focused on specific systems that do not have, in your case, that do not have friction forces or any non-conservative force in them. Right? So what is a conservative force and non-conservative force? I'll just briefly explain them today, and then we'll look at the systems that basically we have a conservation of energy in them. So it's, in a sense, a little easier than the systems we looked at before, because you don't need to be too worried about friction, finding the direction, how to calculate that integral. But there are other obviously things that play, and you have to be careful about. These systems can be more complicated, and by complicated I mean more things that can go wrong. So you have to be very methodological with this approach. I'll go over examples obviously today and next lecture, and we'll look at specific cases, how to deal with them. But one thing I can tell you as general is it's supposed to be easier than the general approach, because we know that we don't really have any friction or any kind of non-conservative force. All right, so let's just get started. Put this under conservation of energy. I guess let's write it this way: conservation of energy. Conservation of energy. Conservation of, let's be more specific, mechanical energy. Even that might not be enough specific, but that's good for a title. So let's start with what I was basically mentioning: conservative forces and non-conservative forces. Now, what is a conservative force? Basically, in a nutshell, or in brief, a force, we say a force is conservative if the work that it performs or its work depends only on the initial and final position of the point that the force is applied. Right. So remember when we were in previous examples so far in energy method, we are looking at where the particle is at point A and where it is at point B, right? And for instance, think about energy, kinetic energy, right? 1/2 mv². We only care about velocity at point A and velocity at point B. Right? Or weight, right? We only care about initial height and final height, and we could find delta H, right? Whether it's going up or it's going down. Or a spring. Right? We only cared about where we are at point A and where we are at point B, and we cared about how much the spring is stretched at point A or point 1, how much the spring is stretched at point 2. We didn't care about what is going on in between. Right? All we were focused on is what is happening at point A, or point 1, sorry. What is happening at point 2? That information was enough for us to calculate those forces that I just mentioned. So those are conservative forces, meaning that when we look at the work done by these forces, only initial and final position characteristics, you can think about it this way, matters. As opposed to that, if you look at friction, then it matters what happens in between. We cared about delta R or dr. Remember, we were calculating FDR. And we cared about how we go from point 1 to point 2, or we cared about what's going on in between. Right? The path matter. Path we take from point 1 to point 2, it matters. Right? Because that determines delta R or dr. So that's a non-conservative force. So let's write it this way: conservative force is How should I define? Is a force, let's put it this way, is a force that its work depends only on the initial and final positions of its point of application. Examples would be weight. I can probably write it better. Weight, spring, force of spring. That's what I remember. Also, you can, in parentheses, you can write example of a non-conservative force, friction. Right? So if you want to think it the other way, in a different way, is that non-conservative forces take energy away from the system. Right now, we are focused on the concept of energy, right? In this part of the course, right? We're looking at energy. So non-conservative forces take the energy away from the system. When you're pushing something, push a box on the floor and trying to move it from one place to another, right? Friction, whatever force you apply, friction is resisting the motion. If you're applying 20 newtons, part of it is gonna be wasted because of friction. So friction is taking away the energy that you're putting into the system to perform work. So it's a non-conservative force. Another example of non-conservative force would be when, look, I think a year from this year, like in a senior year, when you take vibrations. Another example of non-conservative force would be damping. Right? Damping is also a kind of force, is more general concept that takes energy away from the system. And you will see that actually friction can be modeled as a form of damping, but that's a different story for a different force. For now, a good example of non-conservative force would be friction. Now, also let's define, we've been talking about work and kinetic energy. So let's also define potential energy. Potential energy. Now, the way you can look at potential energy is the capacity of a conservative force to do work. Right? Now, if you have a conservative force, that force has some capacity to do work. Non-conservative forces, we don't care because they take away energy. They take this energy away from the system. So, for instance, imagine that you have a spring. Right? When you apply force to a spring and compress it, right, you are storing energy in that spring. So there is potential energy in your spring. So the force you applied, right, it's stored in the spring as a form of potential energy. Now, this potential energy has the capacity to do work. How? If you let that go, the spring is going to be on a stretch, right? It's going to push to go back to its natural length. It's a spring always wants to go back to its natural length. Or think about lifting a weight, right? If you lift a weight from, I don't know, lift it 2 meters up, right? 1 meter up, 50 centimeters up. The force you're applying to lift it up, it's stored in that weight as a potential energy. Now, that potential energy has the capacity to do work. What is the example of it? If you let that weight go, right? It falls. It starts accelerating. So there is some energy there. That energy is being converted into work. So that's the definition of potential energy. Let's write it this way: is the capacity of a conservative force to do work. Right. Now, once we're comfortable with these, now we can look at principle of conservation of energy. What is that principle? Very simple. That principle tells us that the total energy of the system, the sum of all forms of energy, could be electrical energy, kinetic energy, potential energy, remains constant. You've dealt with this before, I believe probably in thermodynamics. The principle of conservation of energy. Just put it here, just to, for the sake of completeness. So, principle of conservation of energy is the total energy, in parentheses, the sum of all forms of energy, right, remains constant. I guess I just review that. I believe that you've seen this in thermodynamics. Now, for closed systems, right? Again, some I guess thermodynamics again is still in play. For closed systems, we can easily say, well, if we go from point 1 to point 2, well, principle of conservation of energy tells us that the energy should be the same. Right? We were talking about conservative forces. So you can think about it this way, or let's write it this way first. In mechanical not mechanical, in this course, let's say, not at the end, I'll just separate it. In this course, I just want to put it here. In this course, we focus on kinetic and potential energy, basically. Kinetic plus potential energy. And you can think about all these as mechanical, because as I said, we're talking about all forms of energy. It can be electrical energy, and that's a whole different story. That's not what we're going to talk about here. The principle of conservation of energy is very general. In this course, we just talk about kinetic and potential energy. Remember, potential energy is just defined as the capacity of conservative force. So we are focused on conservative forces, right? Now, for a closed system, when we go from point 1 to point 2, basically we can just say energy at point 1 should be equal to energy at point 2. All right, simple as that. If it stays constant, then it shouldn't change no matter what, as long as we don't have any non-conservative force in the system. So energy should be the same, all right, for closed system going from point 1 to point 2, or could be any point. E1 is equal to E2, E being the energy that we're dealing with, mechanical energy. So kinetic energy, we've seen it previously, right? The change in kinetic energy, we've seen it. Basically, kinetic energy is 1/2 mv squared. It really depends on mass and velocity. Potential energy, is, we define it, is the capacity of a conservative force to do work. So whatever work we do on the system, as I said, it's going to be stored in the form of potential energy in that system. So potential energy is basically the same as work. It goes from work to potential energy form. Right? We perform work on a system. That work is going to be stored in the system as potential energy, like that spring being compressed or stretched, or the weight you lift. So you can, let me just put this here, right? This like this. So kinetic energy 1/2 mv squared, the velocity, and potential energy your book used V to represent potential energy, which is a little problematic because we have V for velocity. So to follow what your book does, I'll use V, but what I will do is that I use this V for potential energy, and that V, the other V represents velocity. Just keep that in mind, and I'll try to follow this standard as much as I can, so these two V's are not mixed. Right. So V, you can think about it this way: potential energy from point 1 to point 2 is equal to minus work from point 1 to point 2. We saw this. U from 1 to 2 was the work done on the system from 1 to 2. Right. So what you're saying is that work done becomes potential energy. Right? I put negative there because it goes from one form to another, right? It goes from one, we can think about this way, it goes from one side of the equation to the other side. So potential energy is the negative of work done. Or if you want to think about it in terms of that, in terms of that integral, right? We said U from 1 to 2 is integral from 1 to 2 f dr. So you can think about this as dv is equal to minus f dr. Right? Remember we had U from 1 to 2 is equal to integral from 1 to 2 f dr. Since v is equal to minus U, all dv is minus f dr. Just put it as a reminder from what we had from before. Right? So that being said, I'll write it here. Therefore, think about it this way: E1 is equal to E2. So if E1 is formed by, if each of them is just basically a combination of kinetic and potential energy, you can think about it this way. E1 is equal to E2. So T1 plus V1 is equal to T2 plus V2. And this is what I wanted to get into. So the potential and kinetic energy at point 1 is equal to the potential and kinetic energy at point 2. The principle of conservation of energy. And we don't really have any non-conservative force in the system. Right? That's all. Everything I said, just wanted to get into this point. And probably you might have seen it in physics, I don't know, but it doesn't matter really. That's the whole story. Okay. Now, as always, to make our life easier, and this is, as we said, we are talking about conservative forces, and in this course we only talk about the specific forces, mechanical energy. So we can actually, I can give you a list of forces that you're going to deal with, right? Potential energy created by those forces, or conservative forces. So we have weight. Well, we can have a constant force, right, applied to a system, external force. You can have a weight, or you can have a spring. Pretty much that's it. Right? You can push the system F by some force F. That force is gonna be stored in the system as potential energy. So that force performs work, and that work is stored in the system as potential energy. You can have weight lifting something, you can have a spring, compressing spring or stretching the spring. So let's list them, because that's pretty much all we need to know about these forces. So put it under potential energy of conservative forces. Right? Let's just start with some random force, like external force. This is, let's say, potential energy of a constant force. Potential energy of a constant force. What was that? The work done by constant work was integral from point, let's say R1 to R2 FDR, right? So V from 1 to 2 becomes R negative R1 to R2 FDR. If F is constant, comes out, integral from R1 to R2 dr it becomes delta R. So minus F delta R. So basically, the work done, potential energy of a constant force from point 1 to point 2 is minus F delta R. You only care about position at point 1, position at point 2. As long as you know the force and you know where you are at point 1, where you are at point 2, that's pretty much it. It doesn't matter how you get from point 1 to point 2. The second one would be the potential energy of a weight, right, due to gravity. Right? Think about this: potential energy of a weight due to gravity. So work done from 1 to 2 for gravity we define as minus mg delta h. Right? So the potential energy is from 1 to 2. This way is equal to negative of that, mg delta h. Now, since we define T1 V1 plus T2 V2, right, the general form of the equation, you can write it this way. You can think about it this way: at V1, at point 1, potential energy is mg h1. At point 2, potential energy is mg h2. One thing you have to pay attention between potential energy and work done by gravity, right? You see that negative is gone now. We have to define some reference line or datum, right? Somewhere that the datum is here, and then that's zero potential. So we always define a zero potential somewhere, and then we measure this H1 and H2 with respect to that. When we look at those position of the particle or the object at point 1 and point 2. Before, we were just measuring delta H. We were not really taking any reference line or zero potential, as they call it. Here, you have to define some datum, like some kind of reference line somewhere, and then measure where you are. Let's say this is point 1 and this is point 2, then this becomes your H1, this becomes your H2, if you want to write it for point 1 and point 2. Third one, the last one, is the spring. So potential energy of the spring, energy of a spring. Force of a spring, you've seen it before, right, in statics. Basically, F equals to Ks, K being the stiffness of the spring, S being how much the spring is stretched or compressed, right? The strength of the spring, how much, how far are we from its natural length? In if you want to be more specific, if you actually can draw the force versus how much the spring is stretched, if you can draw something like this being S, and this being force in the spring, you can measure that. Typical springs that we deal with, linear springs, this is the line you'll get. You know, you measure some points. At each point, the amount of force you apply, right? On the right side being the spring is stretched, the spring is stretched. On the left side, the spring is compressed, right? The S is negative. The slope of this line is basically your stiffness. This is your K, stiffness. But generally speaking, this is something you will see again in vibrations. But generally speaking, the force in a spring, right, is equal to Ks. Right? S being the stretch of the spring. This is important, so I'll just put it here. Stretch of a spring. Right? This is not new. Now, knowing the force, we can actually calculate, you know, let's just use what we've actually learned. I don't even need to take that integral. Let's just use what we learned. We found what is the work done by spring. It's basically 1 over 2 minus 1 over 2 K S2 squared minus S1 squared. Right? How much the spring is stretched at 0.1, how much the spring is stretched at 0.2. Right? This we know from before. So from there, you can get actually potential energy. 1 to 2 is 1 over 2K S2 squared minus S1 squared. This is the general formula we get. Let me emphasize this. Now, since we typically write the equation T1 V1 is equal to T2 V2, to just make it a lot easier for you, we can think about the potential energy as 0.1 at 0.1 as V1, right? V1 is going to be 1 over 2K S2 squared, S1 squared, obviously, and V2 is 1 over 2K S2 squared. Now, here is, as I told you before, positive negatives get confusing when you are dealing with systems systems using energy methods. When you are, think about it this way, if you have friction in your system, this is not the way. You have to go back to what you were doing previously. And remember, there we were dealing with work, U, and kinetic energy. So U1 to 2 is equal to 1 over 2 mv squared, 2 squared minus m, 1 over 2 mv1 squared. That was what we were doing before. Now here, just want to clear things up so things don't get confused. Here, we are saying, let's say we don't have any non-conservative force in the system. If we don't, right, T1 V1 is equal to T2 V2. Kinetic energy at 0.1 plus potential energy at 0.1 is equal to kinetic energy at 0.2 plus potential energy at 0.2. Nothing is lost in the system, right? Whatever energy, total energy you had at 0.1 should be equal to whatever energy you have at 0.2. And nothing is taking energy away from the system, no non-conservative force. So we go from work kinetic energy to potential kinetic energy. Potential energy, kinetic energy. Now, potential energy is a negative of work, because whatever work you do on the system is going to be stored in the system as potential energy. A little bit of, again, I don't know, I keep referring to thermodynamics, that's how I remember it. Work done on the system versus work done by the system, you know, that whole positive, negative. You can think about it this way here. The work is stored in the system as potential energy. So now we care about potential energy. So 3 types. This is straightforward. No spring here. No friction here, or non-conservative force. So you either have a constant force, so you can calculate its potential energy. You either have weight, potential energy. You define a reference point or reference line or datum, and with respect to that, you can find potential energy at each point, knowing that height. Spring, how much the spring is stretched at point 1, as long as you know that, S1, that gives you V1. How much the spring is stretched at point 2, that gives you V2. Knowing V1 and V2, remember, the whole idea is to write this equation. I have to, maybe it's better if I do it in red, so you know that this is the whole story. So hopefully that makes sense. What is the difference from previous procedure that we're following, right? All right, let's look at a couple of examples. Obviously, things start making more sense when we see what happens in a system that we typically deal with. Well, let's just start with this example. This has some good, interesting stuff in it. So let's say, any questions so far? The concept makes sense to you? If it doesn't, tell me so I can just try a different way. Because I just don't want confusion between what is happening here versus what we were doing before. We were dealing with work and kinetic energy. Now we're dealing with potential energy and kinetic energy. Why? Because we know there is no non-conservative force to dissipate the energy. So whatever is the kinetic energy should either stay as kinetic energy or be converted into potential energy during the motion. Nothing is wasted. All right. All right. So let's look at this example. We have drawing this. I'm gonna try. So we have this weird shape that is just there to make sure that you're challenged enough. There is no way I can draw this. Let me do this. That I can do. Go here. Huh, not that. And then go there. There we go. Let's see how bad it gets when I'm going to draw this. And then goes from there. So think about this as something thick that is a bar. I'm not going to try to draw a bar because I have to make things parallel. And you know what? Let me just try. Oh, I have to stay on the same side. This is a bar, so it has some thickness. Oh my God, that is going to be challenging. There we go. Let's see if we can do it further away. Obviously, it's not crooked. It's supposed to be straight, but that's as good as I can get. All right, this is a bar. There's a weird shape. It looks like, I don't know if you guys have had fluid mechanics yet. The whole Bernoulli and fluids in pipes. That's how I remember dealing with those problems. Anyway, so we have a slider, right? The slider is here. Let me draw it a different color. I have a slider there. Technically, you shouldn't be able to see the inside, so I'm going to try to erase it. All right, this slider is this is point A, this is point B, this is point C, and this is point D. Let me write the problem statement. This is the bar is smooth, so no friction there, no conservative force, non-conservative force. The almost right. The 10-kilogram slider A, let's put it this way, add A is given a downward velocity of 6.5 meter per second. You do need some dimensions there. So, oh my God, I totally drew it. Yep, that's not how it should be. So, I'm sorry, folks. This is supposed to be this way. It's supposed to be this one. Okay, I can go get a tea or coffee by the time I'm done. It might take some time. All right, that's as good as I can make it, but it's pretty straight and smooth. It doesn't look like that in reality. So that's my version of reality, I guess. So this is the rest of the circle. It's a semicircle, and this is 1 meter, the radius there, and there the radius is, that's supposed to be also a semicircle. The radius here is 1 meter. The height here is 2 meters. All right. So it's given a velocity of 6.5 meters per second. Part A, let's solve part A first. What is the magnitude of the normal force no, that's not part A. Part A should be straightforward. So part A is use conservation of energy to find whether the slider will reach point C. If it does, what is the magnitude of its velocity at point C, at that point, or at point C, right? So finally we got to a point we can solve it. All right, so we have the slider at point A. We know its mass. It's given some initial velocity, 6.5 meters per second downward. Remember, in energy method, as I said before, we only care about, the only thing we can work with is the magnitude of velocity. It's not like Newton's method that we actually could get to what is the direction, or in terms of vector, what is the direction of velocity, what is the angle it creates with some specific direction. Here we just deal with the magnitude of velocity, it's energy method. Right? No direction as far as we're concerned most of the time, at least, unless we can find it by looking at it, right, from what we learned from kinematics. But inherently, energy method is mainly focused on the magnitude of velocity. So use conservation of energy to find whether the slider will reach point C. So what we do is that we're going to assume that it can reach point C, and then we write the conservation of energy equation between point A and point C. Right? If we get some velocity, physically, velocity it has some magnitude, then yes, it does. It gets there, and we know the velocity. If the velocity turns out to be some weird number, like a square root of a negative number, it means it physically is not possible for this to happen. So it doesn't happen. Right? It doesn't reach point C. That's the logic here. So here's how I assume. We assume it reaches point C. If you make the assumption, then we're going to have, this is going to be where we are at the beginning, point 1, and this is going to be where we are at the end. So I'm going to write T1 plus V1 is equal to T2 plus V2. Right? No conservative force and no non-conservative force in the system. Every force is conservative, so we can just write that. All right, so let's just separately find each of them. All right, make sure that we know what we're doing. So T1 and then V1. What is T1? T1. What is T1? T1. It's basically this kinetic energy at point 1, right? Going back to what we talked about. I did not bring the kinetic energy here again, right? I just assumed that we have it from before. So just maybe you want to add it somewhere to have your notes complete. Actually, I did. Why am I confused? I did right here. I just did not box it here. It's kinetic energy. 1 over 2 mv squared. We already know it from before. So at point 1, we have 1 over 2 m v1 squared, and we can actually calculate that. We kind of know everything. We know the mass of the object, we know the velocity, and the velocity is actually, let me write it like this, is va squared. So that would be 1 over 2 m is 10 kilograms. Velocity is 6.5 squared. Now, looking at potential energy, we have a list of forces that we have to double check. Right? We don't really have any constant force. Nothing really is applied to it, just gave it an initial velocity. We do have weight. Well, the height is changing, so that's something we have to take into account. And we don't really have a spring. So the only thing that we have to think about is the potential energy of the weight, or due to gravity. That's what I'm going to do. To do that, as I said, I have to define some reference, zero potential. Now, typically the easiest way to do this, you can take your zero potential wherever you want, right? As long as the dimensions let you find the height at each point, you're good, right? I suggest typically it's easier to either take point 1 or point 2 as your reference point. Now, that's not the rule. Right? You might play around with it depending on where is easier and where we have more information or dimensions. But in this case, it's easier to take this as your zero potential, right? Or data. Think about this as zero potential. If that's zero potential, height at point A is 0, so you get mg h1, your h1 being 0, this becomes 0. Right? This is 0. Because I took the datum there. You could come and say, well, I want to take 0 potential here. That would have worked. I would have stopped you from doing that. If you put 0 potential here, then your H1 would have been 1. So you had some potential energy due to weight at that point. I took Hilbert point A is, so that makes my life easier. More 0 in equations, the better. Point 2, right? Point 2, T2. Well, we don't know what is the velocity at point 2. So 1 over 2 mv, I'll say vc squared. That's we're assuming we're reaching point C and it has some velocity. So we'll leave it there. V2 is, well, how far we go from the 0 potential or datum, 2 meters. So that would be mg h2 being 2 meters in this case, given that line as a reference point. So this becomes 2 mg. Let's write everything in terms of m, so we can actually get rid of m. So I can form this equation now, knowing everything. I know t is equal to 1 over 2. I'm going to just write it in parametric, using the parameters instead of putting numbers. V1 is 0, so nothing there. T2 is 1 over 2 m Vc squared plus 2 mg. Well, I can cancel out m values there. So even if you are not given m, you could still find what you're asked to find. Vc is equal to, that goes to the other side, square root of Va squared minus 4g. Now calculate this. If this is positive, then yes, your assumption was right. The slider reaches point C, and that would be the velocity. If it turned out to be some weird number, negative, a square root of negative would have been a complex value that doesn't make sense, right? You know, physically doesn't make sense. So the assumption was wrong, and it doesn't reach point C. VA is 6.5 squared. Well, we know G. I'll give you, if my calculation is right, is 1.73 meter per second. So it's a meaningful number, which means that we reach point C, and this is the velocity at point C, right? Velocity at point C. That's part A. Now, a question about this one. So, things you have to pay attention when you're dealing with weight. Find the 0 potential, datum, reference point, reference line, whatever you want to call it. Measure the potential or calculate the potential energy due to weight with respect to that. Obviously, this geometry is going to come into play. Some playing around with dimensions to make sure you get the right height. Kinetic energy is just kinetic energy. It's really not that much there to play around with. All right, I'm going to give you a few seconds if you're taking notes. Or a question that might come. All right. Let's do part B. It's a little more, I guess, exciting. At least it gets into what we've learned from before. So part B tells us, it's asking us to find the magnitude of the force, right? It's let me write it. What is the magnitude of the normal force the bar exerts on the slider as it passes point B. So here's what we're asked to do. We are asked. It says, well, we have given some initial velocity downward. It's going through this. This slider is going or following this bar. Now, when it gets to point B, somehow I erased it from here. This is point B. When it gets to point B, the slider gets to point B, we are asked to find the force that is applied by the bar to the slider, exactly at that point. So now we can do it in reverse, right? Let's say we want to find it. Let's draw the free body diagram of a kinetic diagram of slider when it reaches point B. Right? I'm going to draw it here. This will be M. So when it gets to it reaches point B, let me try to draw it here. This is slider at point B. When it reaches point B, well, think about this as a motion in a circular path, right? This is a semicircle. We know it's a radius. So one way I can deal with it is to take tangent normal coordinate system. Forces applied to this, well, there is no friction. So the only thing that is applied to this slider is the normal force from the bar and also the weight downward. So here's what I'll just put them here. This is normal force and this is weight. mg, this is normal force. Right? That's pretty much all the forces we have in this scenario. But exactly, you're right there at the bottom. Everything is like weight is downward, n is upward. N is normal force, smooth surface is always perpendicular to the object, perpendicular to the surface applied to the object at the point of contact. Now, if I use tangent normal coordinate system, it's moving this way, so direction of the motion is this way, so ET, this is toward the concave direction, EN. So following that logic, this becomes, these are the components of acceleration, or these are what I have on my kinetic diagram. Right? MAT, MAN. If I, well, nothing really, I put MAT there, but you can see that there is actually at exactly that moment, nothing there, right, in tangential direction. So looks a little awkward because we don't really have friction there, the assumption. So, but just focus on normal direction. Right? So if I write summation of forces in normal direction, what do we get? We get summation of forces in normal direction. It would be MAN. I got upward is positive, so N minus mg becomes equal to MAN. Right? This is what I get. Now AN is, we had it as, you can either write it as R omega squared or V squared over R. That's what I wanted to get now. We don't know N, that's what we want to find. Mg is mg, we know M. Missing is normal acceleration. What is missing? And normal acceleration is v squared over r. R we know, v we don't know. And that v is v at point B. Right? This is velocity at point B. So velocity at point B, we can find that using energy method now. Right? So that things are getting interesting, right? Now, whatever we've learned before, assume that you had no idea that this is about energy method. You just draw free body diagrams and write the equations. We get to this point that you need a velocity. Or everything is there, missing point is velocity. So now we can use energy method. Given the information you have, right? You can actually, what is going on at point A. There is no non-conservative force in the system, so you can find the velocity at point B. Right? All you got to do is that, so we use conservation of energy to find VB, velocity at point B. Let's go back there. Now we have, let me use a different color. We have point A. Point 1 is still point 1, and this is our point 2. T1 plus V1 is equal to T2 plus V2. Just pay attention that V1 and 2 has changed now. This is the second set. Let me write it this way: between so later on 1 and 2. These are 1 and 2 now. This color. So T1 plus V1 is equal to T2 plus V2. T1 is 1 over 2 m VA squared. V1, let's use the same datum, I guess. Let's just not move it. You could move it. It doesn't have to be the same zero potential. I'm just going to use the same zero potential. So V1 is 0. T2, well, 1 over 2 m VB squared. That's something we're trying to find. And V2 is, well, if that's my datum zero potential, I went down 1 meter at point B, so that becomes minus, it becomes mg h2. H2 is -1. Remember, now we have a reference. Becomes -1. That becomes mg h2. This is -1. So this becomes minus mg. Putting this together, T1 plus V1 is equal to T2 plus V2, right? From there, you will get 1 over 2 m VA squared is equal to 1 over 2 m VB squared minus mg. From there, the only thing you don't know is VB, which you're trying to find. You can get rid of m values pretty much. There you'll get VA squared plus 2g. That will give you, VA 6.5, right? VA is 6.5, so this becomes 6.5 squared. G is G. The value for VB becomes 7.87 meter per second. This is the velocity at point B. Once you know velocity at point B, we'll go back to what we started, where we started, right? This equation. So let me go to the next slide. So from star, why they changed it? From star and knowing VB, right? What we get is N becomes mg plus an. An is VB squared over R, so you'll get this. You'll get N is equal to mg plus, let me just write it this way first, and then mg plus VB squared over R. And you know the values, you know, M is 10 kilogram, you know, VB now is 7.87. So 7.87 squared, R is 1. From there, you can find your normal force. And I think that'll give you, hopefully it's right, 717 newtons. I'll go back if you were writing, just no problem. So I wanted the force. I started with Newton's method, right? I wrote a free body diagram because I had to find the force. I got to a point using whatever we learned, kinematics, right? And generally dynamics, kinematics and kinetics. We realized we need a velocity at this point, at point B. We used energy method or conservation of energy to find the velocity at point B. All right. A couple more examples. Let's see. What time is it? Maybe I should just put the problem statement, then we'll solve it in the next class. Let me just write the problem statement, so it's going to save us some time. Just going to wait here a few minutes. Any question on this one before I even move? Usually, energy method is relatively straightforward, especially if there is no friction in the system. All you have to do is to be very careful about dimensions. As always, you always have to be careful about dimensions. How to find out where you are. Next example would be related to springs, so we'll see. You have to. Sorry, go ahead. Great.
Wouldn't you be subtracting gravity?
Did I make a mistake somewhere? Well, I moved mg to the right side.
Oh,
Subtracted, right? N minus mg is equal to ma from here. Right?
okay.
And then I said n is equal to mg plus man. I factored out m. I just skipped a few steps.
Okay.
All right, let me just write the problem statement. Let's see the next example. Then we'll solve the next class. So, no question on this one. We're good. So next example, we have another bar again. We have a mass slider here, and then the slider goes there, or we have to say it goes from there to here. Let me try to see if I can remove the part inside there. We have, let's put it here. It's supposed to be straight, but I guess you get the idea. So the spring is attached to this. This is spring, and then you can think about it as position 2. Maybe I should have tried a different color. So those are not two masses. It just goes from 2 to 1, 1 to 2. This height is given on this height. and this dimension is given. This is 600 millimeters. This is 300 millimeters. The problem statement says when the 1 kilogram color is in position 1, and that being position 1, this being position 2. Spring has a stiffness K. Position 1, the tension in the spring is 50 Newton, and the unstretched length of the spring is 260 millimeters. If the collar is pulled to position 2, I just pull it that way, and released from rest, what is its velocity when it returns to position 1, right? All right, that's pretty much